Couple days we've been talking about the Laplace transform, and once again the concept of transform is we're going from one sort of set of inputs to a different set of inputs. So Laplace starts off in what we're going to call the time domain and sends you over into a frequency domain. All right, and doing a deeper dive onto what this S means, that'd be a good project, right? This is like a complex frequency, and then you could talk about how it factors into the Fourier transform, things like that, right? Ultimately, we're going to take an initial value problem, and this is what we'll do next week. We'll take an initial value problem in the time domain, and then we'll Laplace it over, and we'll get an algebraic problem in the S domain, and then we'll solve it here, and then we'll want to bring it back. And so the way we're going to bring stuff back is with the inverse Laplace transform, right? So in the same way that integration and differentiation are inverse processes, Laplace and inverse Laplace are inverse processes. So basically what we're doing here in section 8.2 is we're going to reverse the Laplace transform. All right. So for example, we know the Laplace transform of e to the 2t is 1 over s minus 2. So the inverse Laplace of 1 over s minus 2 is equal to 2t. All right. Now the way we're going to do the inverse Laplace transform is we're just going to just reverse the formulas, right? Just a second here. Okay. So that's how we're going to do it. But there is, and this is another project, there is a way to get the inverse Laplace as an integral. But the integral is over the complex numbers. So I think I make a note of that later on. So pretty much here's what we're going to do. The Laplace transform of t to the n power, we know that that's n factorial over s to the n plus 1. So the power on n goes up by 1, and you multiply by n factorial. So if we're trying to bring back a 1 over s to the n, that's going to come from the power less than n, 1 power less, and then to counteract multiplying by that power, we're going to divide by that power. Okay? So this is like when you put on your socks and then put on your shoes. To reverse that process, you take off your shoes, then you take off your socks. You do the opposite in the opposite order. And then the same thing here. So all of these formulas come from reversing the formulas that we talked about yesterday. Okay. The best way to learn these formulas, you can make flashcards. So I mentioned if you have like a flashcard with the Laplace on them, then on the reverse you could do the corresponding inverse Laplace. Linearity, the inverse Laplace transform is linear. And then we have the forward shift. So yesterday we had the forward shift. If you're multiplying by e to the at, so this is the last thing we talked about yesterday. That's going to be the same as the Laplace of just that function, but we shift the s to s minus a. So we can reverse that process. And there's a couple different ways to think about that. If you start with something that's obviously been shifted, you can pull that out as a factor of e to the at. Or, I think this is a better way to think about it. And we'll see use of this here at the end of class today. But the inverse Laplace of something, we can factor out an e to the at, and then replace the s with s plus a. So we'll see this in our last couple examples. And so once again, this is an interesting project idea here. Is what's the inverse Laplace look like? And once again, how does that tie in with the Fourier transform? All right, so here we go. So find the inverse Laplace transforms. So that's why I think tomorrow we're going to have a work day, because you need to have time to practice Laplace and inverse Laplace before we start solving diffie-qs with them, which we'll do next week. So you want to take this time to really kind of practice these. And once again, if you look on the Blackboard site there's links to extra practice from Paul's online notes or some extra problems there you can look at. But a lot of this is just coming back to, remembering taking the Laplace transform and then what sorts of things, like where does an s over s squared plus 4 come from? Well, we got a sum of squares on the bottom, s squared plus 4. That means it's going to come from a sine or a cosine. And since it's an s on top, it's coming from a cosine. So if you remember this, this was the frequency squared. So that would be like your k squared. So we have an s squared plus k squared in the denominator, s on top. So this is going to come right back from a cosine. K squared is 4, so that would be k is 2. Right? And the way you check your answer is you would start with your answer and take the Laplace transform and see that you get your answer. So in the same way, when I always teach antiderivatives and integrals in calculus, you can always look in the back of the book to check your answer, but the best way to check your answer is to take the derivative. The same thing here. The best way to check your inverse Laplace is to take your Laplace. That'll help you practice even more. Next example here, we've got a difference of squares in the denominator. So that means we're coming back to a sinh or a cosh. Since we don't have an s in the numerator, that means it's coming from a sinh. So this is coming from a sinh of, and once again, that squared there, that's the square. So it would be sinh of 3t. But if I took the Laplace of sinh of 3t, I would also get a factor of 3 in the numerator. So to counteract that, I would divide by that factor of 3. And once again, you can check your answer by taking the Laplace. All right, the next example here, we've got the inverse Laplace. We're taking the difference of two functions, but just like the Laplace, the inverse Laplace is linear. So this can be the inverse Laplace of 1 over s plus 3 minus 2 times the inverse Laplace of 1 over s to the 4th. So now we think backwards. If we've got a linear factor, 1 over s plus 3, that's coming from an exponential, 1 over s minus a. So this is s minus a negative 3. So that's going to come back to an e to the minus 3t minus 2 times the s to the 4th. And s to the 4th is going to come from a t cubed. But when you Laplace the t cubed, you're going to get a numerator of 3 factorial. So in order to counteract multiplying by 3 factorial, we divide. Yeah, this is inverse, thank you. So we would divide by 3 factorial. Okay. So once again, you can memorize the formulas for inverse Laplace, or you can just think your way through reversing the process, whatever works for you. And we can simplify this. E to the minus 3t. 3 factorial is 6, 2 over 6. So minus t cubed over 3. Now, since the inverse Laplace is an integral, you can use a lot of the techniques you use for integration to help you figure out things to do in trying to find these inverse Laplace transforms. So for example, on this next one here, you got the inverse Laplace of 3s minus 1. So one of the basic techniques of integration is you can they call it separating the numerator. It's really just using the distributive property. But if you have 2 terms in the numerator, in the denominator, you know how you can handle that denominator. What you can do is you can just rewrite this like you would with an integral. And on this first term here, you've got that 3, which is a constant, so you can bring that out via linearity. And you note the denominators here, we've got a sum of squares. So when you have a sum of squares in the denominator, you're thinking sines or cosines. This has an s in the numerator, so that's going to come back to a cosine. The frequency gets squared here. So this would come back to a 3 cosine of 2t minus, this would have, there's no s in the numerator, so this would be coming from a sine of 2t. But when you Laplace the sine of 2t, you'd have a factor of 2 in the numerator. So that would come back, whoops. We'd have to counteract that by putting a factor of a half. Do you get the gist of what's going on here? Do you see what's happening? We're just reversing, we're reversing all the formulas we learned in section 8.1 is what we're doing. All right, so yesterday I mentioned we'll be using partial fractions to help you find inverse Laplace transforms, because we're going to, we start with this here, and we're trying to think, well, what does that come back to? Because if you think about the formulas we know, if you look at the formulas we know for the inverse Laplace, we are good with powers of s in the denominator. We're good with linear factors s minus a, and we're good with these sorts of quadratic factors. All right. None of these things covers this scenario because we've got a quadratic with a middle term. You follow? If that s weren't there, we could bring it back. It'd be some kind of hyperbolic sign at that point. So we're going to use partial fractions. So if we want to do the inverse Laplace of 10 over s squared minus s minus 6, once again, we can think of partial fractions. So the first step of partial fractions is to do what with the denominator? Yeah, we're going to factor it and then we'll separate it. So factoring here, does that factor nicely for us? Yeah, s minus 3s plus 2, good. So now I have to think what sorts of little denominators would contribute to this as the common denominator. So we would have an a over s minus 3 and a b over s plus 2. And at this point, you can use the Heaviside method that I mentioned in a video there. You don't have to, though. Heaviside works in particular cases, but not all cases. The way you probably learn to do this is you multiply both sides by the denominator here. So when you multiply by s minus 3 times s plus 2, s minus 3 cancels here, you're left with s plus 2. S plus 2 cancels, we get s minus 3. And then you can sort of cheese your way to these coefficients by picking good values of s. So what would be a good value of s to plug into this to help you recover one of the coefficients? I could plug in s equals negative 2. If I plug in s equals negative 2 to the left-hand side, I just get 10. When I plug in s equals negative 2 to the right-hand side, this factor is going to cancel out, and I'll just be left with b. So what do I get for b then? Yeah, good, negative 2. All right. Now, what's another good value of s to plug in to cheese an answer out? Three is a good one, too. If you plug 3 in, that'll cancel out the b term. The left-hand side is going to be 10. It's going to be a times 3 plus 2. So what do I get for a here? 2. Okay. Or you can use that Heaviside method. The way the Heaviside method would work is you would look at what value of s makes this 0, and the answer is s equals 3. You would cover up the s minus 3 and plug 3 into what's left over. So a would be 10 over 3 plus 2, so a would be 2. And then here you would look at what value of s makes this 0, negative 2. Cover up the negative 2 factor over here. Plug negative 2 in, and that would recover b. So that's the Heaviside method, but I have a video on that. Any questions on that partial fraction decomposition? You're gonna be doing this a lot. So what this means for us is that the inverse Laplace of 10 over s squared minus s minus 6 is the same as the inverse Laplace of a over s minus 3, so 2 over s minus 3, plus b plus a negative 2, so minus 2 over s plus 2. And now I've got a difference here of 2 linear factors in the denominator. And so I can, once again, apply linearity. So 2 inverse Laplace, 1 over s minus 3, minus 2 inverse Laplace, 1 over s plus 2. And now I can use the formula here. Inverse Laplace of 1 over s minus a is e to the at. So here it's s minus 3, so that's going to come back as 2 e to the 3t minus 2. And what's the a here? Since it's s plus 2, it's going to be e to the minus 2t. Very good. And once again, the ultimate check is to start with this. Take the Laplace transform. You'd use linearity. You'd get back to here, and then you'd have to reverse the partial fraction decomposition process, right? So if you start here, you would use linearity. You get to this, and then you'd have to get a common denominator. So right, partial fraction decomposition is just reversing the common denominator process. Any questions on this example? This is a little more than just formulas. You got to do some algebra first. Just like any good math class, 95% of what we're doing here is algebra. Really, there's no calculus even in this. It's just formulas at this point. All right, let's take a look at this next one here. We've got inverse Laplace of s squared plus 27 over s cubed plus 9s. Now you might think, well, let's try separating the numerator. If we look here, we don't really know what to do with this denominator. This denominator isn't the sum of squares. If this denominator were, something different, maybe we would try something like that. Like if this were an s plus 27 over s squared plus 9, separating the numerator would probably be a good idea here. But since our denominator's got more than a quadratic, let's go ahead and just try to partial fraction it. So how do I factor this denominator? What's the furthest I can break that down? Yeah, take out that s. And this is an irreducible quadratic, right? So irreducible quadratics are quadratics where you have non-real zeros. Yeah. So we're going to leave that there. And we're just going to do this. Now, if you wanted to, you could break it down with the imaginaries. And then when you bring stuff back, you can combine those complex exponentials into like sines and cosines. But we're going to just stick with real numbers right for now and break it down. So once again, we can go ahead and clear denominators here. I would get an s squared plus 27. A times what? What would be left over here if you multiply that denominator through and you hit that first term? What's going to be left? S squared plus 9 plus the quantity, don't forget parentheses, bs plus c, and that's going to get multiplied by what? S. So first thing we ask, is there a value of s we can use? Oh, because this is an irreducible quadratic down here. So we're trying to think of the types of fractions that could combine to get us this. And so since we have a denominator of s squared, the numerator is a bs plus a c. That's what makes it a proper algebraic fraction, is the degree on the numerator is less than the degree on the denominator. So that's your partial fraction decomposition stuff. If you want, Thomas, I can send you, I'll send you a video that kind of reviews the partial fraction stuff. It's probably up on Blackboard. But yeah, that's it. Irreducible quadratic denominator gives you a generic linear numerator. Any linear or repeated linear denominator just gives you a constant. All right, is there a value of s we can use to cheese this? Is there a value of s I can plug in that'll help me get one of these a, b's, or c's? Yeah, 0 works. 0 is a good one. Because if I plug in s equals 0 on the left-hand side, I'm going to get 27. On the right-hand side, I'm going to get 9a. But because this s is multiplying all of this, you're going to get a 0. So that gives a is 3. So that's nice. Now, in order to get the other two, you could plug in different values of s, or you can do what I like to do, just equate coefficients. So let's talk about that. So equating coefficients, that's the same thing we use when we do undetermined coefficients. Equating coefficients is just a statement about linear independence of these functions. So let's talk about equating coefficients. On the left-hand side, I got s squared plus 27. On the right-hand side, I would have as squared plus 9a. We'll plug in a here in a minute. Plus bs squared plus cs. Okay. So if I look at equating coefficients, what I do is I look at the powers of s on both sides. So here, s squared, on the left-hand side, I've got 1s squared. On the right-hand side, I'd have as squared plus bs squared. But I just found out a was 3. So what do I get for b here, folks? -2. I know. The cat's excited about partial fractions. All right, now I look at the s terms. On the left-hand side, there's no s's at all. On the right-hand side, there's just c of them. That tells me c is 0. And then pretty much I'm done. The last step would just be confirming that a check on the constants. We'll just do this for completion, but we kind of already did this already. If I look at the constants, I get 27 equals 9a, but I already knew that a was 3. So you can actually do all of them that way if you want. So if you can't cheese out the coefficients, you can equate coefficients. That'll get them to you just as fast. So what's the long and short of it? So we had the inverse Laplace of s squared plus 27 over s cubed plus 9s equals. And now I'm going to hit this with the partial fraction decomposition. It's a over s, so that's 3 over s, minus bs plus c. So b was minus 2, c was 0, so minus 2s over s squared plus 9. Right? And so what we've done is partial fractions allows us to rewrite the function as a linear combination of functions that we know how to find the inverse Laplace of. So I can hit linearity here. This is 3 inverse Laplace of 1 over s minus 2 inverse Laplace s over s squared plus 9. And what's the inverse Laplace of 1 over s? That's just 1. If you really want to think about it, if you want to be pedantic about it, you could write this as s to the first power. That comes back t to the 0 over 0 factorial, which is 1. Or you could just remember that 1 went to 1 over s. So I got 3 times 1 here, minus 2. I've got a sum of squares in the denominator, so that makes me think sine or cosine. There's an s in the numerator, so it's cosine. And the frequency here would be the square root of 9, which is 3. And so there's our inverse Laplace. Okay. So I'll double check if the partial fraction, I know the partial fraction decomposition, I think it was up there for chapter 2. Because we were doing some stuff in chapter 2. But if not, I'll just copy it and put it in here with the other stuff. So I'll have some resources for you. This is one of the reasons I think it's good to just have a work day tomorrow, to give you folks a chance to get caught up on your Laplace and inverse Laplace before we move into stuff next week. Because otherwise you just feel like you're constantly behind, and it's just not a good scene. All right, let's take a look at this last one here in this example. So here we got an s to the 4th down there, plus 4s squared, plus 3. Once again, none of our basic formulas addresses this, because we got s to the 4th down there. So we got to rewrite it to use what we know. So once again, first step in partial fraction decomposition is to factor that denominator. It's got 3 terms, and the exponent here is twice the exponent here. So this is one of these things I like to, when I teach this in the algebra, I call this a quadratic in disguise. It takes me back to my youth when we had transformers and they were robots in disguise. So you've got 3 terms, and the power on one is twice the power on the other. That means you can try to factor this by doing your usual unfoiling types of things. You can just cut that in half. Instead of trying to factor it as s and s, you can factor this as s squared and s squared. Why? Because all you've got is an s squared there. So with that, how does this break down? I need factors of 3 that add up to 4. Yeah, 1 and 3. So s plus 1, s squared plus 3. Now, both of these are irreducible quadratics, meaning that if you try to find their zeros, find their roots, they're non-real. That means that they're going to come from, an s squared plus 1 and an s squared plus 3, but we have to have proper fractions there. So the numerator here, once again, this could be a generic linear function, and this can be another generic linear function. Put those up there. All right, so step 1 is to clear out the denominators. So on the first term, the as plus b, when I multiply through by both of these factors, the s squared plus 3 is going to be left to multiply. s squared plus 1. All right. If you try to figure out an s that's going to wipe everything out except one of them, I don't think you're going to have much success here on this. So at this point, you would just go to equating coefficients. So to do that, let's go ahead and write out what we would get here. We would have an as cubed plus a 3as plus a bs squared plus a 3b plus a cs cubed plus a cs plus a ds squared plus a d. And so what we're going to do is take advantage of linear independence of different powers of s, and we'll equate coefficients. So we start off with the highest power of s up here. That's going to be s cubed. On the left-hand side, you got no s cubes. What would be, how many s cubes would we get on the right-hand side? Well, there's two terms with s cubes, but there'd be a plus c of them. Yep. So I got 0 on the left, and there's a plus c of them on the right. S squareds, once again, there's no s squareds on the left. On the right, what would we get? A b and a d added together. And now for s's, got no s's on the left. What do we get for s's on the right? Yeah, 3a plus c. Here comes the cat again. And then for constants, we've got 1 on the left, and that's going to have to equal what? What do I get on the right? 3b plus d. So here you get a and c are opposites. Here you get d and b are opposites. So now let's see, if c is minus a, this would say that 3a minus a is 0. That's going to give us that a is what? 0. Which means c is also going to be what? 0. And then we've got this one here, d is minus b. So 1 is going to be 3b minus b. This gives us b is what? A half. And since d is minus b, that means d is going to be minus a half. All right, so you get these equations, and hopefully you remember these from either earlier in this semester or back to your calculus class. But there you go. So that's the algebra part. So how does this help us? This helps us rewrite. We're trying to find the inverse Laplace transform of 1 over s to the 4th plus s squared plus 4s squared plus 3. Which we don't know how to do, but we've resolved this into partial fractions. This is as plus b. A is 0, b is a half. So this is a half over s squared plus 1. C was 0, D is minus a half over s squared plus 3. And so this comes back to a sine. This would be because we have a sum of squares with no s on top. Frequency 1. So sine of t minus a half. This would be a sine. This is the frequency squared, remember. So that would be t root 3. But if I took the Laplace of this, I'd have a root 3 multiple. So I'd have to divide it out. Okay. So partial fractions, and then use the formulas. All right. So in this last example here, we've got denominators that have irreducible quadratics that aren't just two terms. So if you have irreducible quadratics like an s squared plus an a squared, then you know that's your sine or cosine. But if I look at this one here, s squared minus 4s plus 13, and I you know, it doesn't factor nicely because the only two nice factors, quote unquote, of 13 are 1 and 13. You can actually check, and I know the mentor folks are going to have to dash here. You can check the discriminant here, and you're going to get a negative number, all right? Because you're going to get 16 minus whatever it is, 52. So it's a negative number. So that means this is an irreducible quadratic. We have non-real zeros here. So when that happens, we want to complete the square. So once again, this should take you back to like when you were integrating stuff, integrating with partial fractions. So we want to complete this square, and this is where that shift property is going to come into play. So, you know, I don't know how people get taught different ways to do different things. The way completing the square typically works is that if you have like an s squared plus a b times s, as long as it's coefficient 1, this is the recipe for that. Some people actually draw a square, which I think is cool. Yep, thanks Abby, thanks Zaran. You can just finish. We'll have a work day tomorrow, so if you have questions, you can come in and ask. That's the recipe for completing the square. You can get this from actually looking at a square and completing it, which is fun. You got your, you know. But whatever. However you get it, it's fine. Sometimes you can just look at it. But in this particular case, you got s squared minus 4s plus 13. Since that s has a coefficient of 1, we can go ahead and apply the formula here. You cut this in half. So half of negative 4 is negative 2. And then you subtract off that thing squared. So you get s minus 2 squared plus 9. Right? And the ultimate check is to actually write this out. If you actually FOIL this out, you'd get your s squared minus your 4s plus 2 squared. So that minus 2 squared here is to counteract that term you're adding in there. So you're adding in a term to complete the square, and then that takes care of it. Okay? So this is the best way to check completing the square, is just multiply it out. But anytime you see an s there in parentheses like that, this is indicating a shift. So that's your big clue that we want to use that shift. So there's a couple different ways to think about that shift. In this particular case, you might just think back to what we did yesterday. The inverse Laplace of f of s minus a is you pull out e to the at and just Laplace what's left over. So in this particular case, the only place we've got an s is in that quantity that's being shifted. So this is probably the best way to handle this. So that s minus 2, I can just factor that out in a way from the inverse Laplace. It'd be an e to the 2t, and then the inverse Laplace is I just would have the s there. So I take care of the shift on the s that way. And then I look at this, and it's a sum of squares. There's no s on the top. So the sum of squares tells me it's a sine or cosine. Frequency, square root 9, which is 3. Since there's no s in the numerator, that means it's going to come back as a sine. Frequency 3, square root 9 is 3. But if I took the Laplace of sine of 3t, I'd have a multiple, a factor of 3 come out. So to counteract that, I would have a denominator of 3. So you see how to identify this shift? This is one way to handle the shift. Now the other way to handle the shift is to use the shift property this way. Here's how we could look at what we have here and apply this formula. It comes down to personal preference. You see that s minus 2 makes you think of a shift, so that would be e to the 2t inverse Laplace, and then I replace s with s plus 2. And so then it gets you back to the same place. It's an equivalent formula, right? Just depends on how you recognize it and how you see it. Where this version of the formula really helps out is in examples like the next one, right? But once again, the cue that you're going to be using a shift is when you have to complete the square. If you complete the square and you have something like this going on, that's your cue to use the shift. Okay. Like on this next one. So if you notice, this next one, as if contrived by design, it's got the exact same denominator as the first one. So it's an irreducible quadratic down there. And so we're going to have to complete the square. And so it's the same complete square that I had before. It's as if I could predict this would be the last example with 5 minutes to go in the class. So you complete the square as normal. And this is where that other formulation of the shift I think is very helpful, because it's easy to make a common mistake here. So once again, you complete the square, you've got an s minus something in a quantity. That means we're going to use that shift formula. So I'm going to pull out an e to the 2t times inverse Laplace. And this is where I think it's helpful to replace s with, in this case, s plus 2. Because not only do you have the s down here in the quantity, you see we got an s up here. That's not in a parentheses. So this is what we're going to do. We're going to replace s with s plus 2. So this is where I think the other version of that shift formula is helpful, because it's going to remind you that you have to account for this s as well as this s. The common mistake students will make is they'll factor out that e to the 2t to fix what's down here, and then they'll completely forget that there's an s up here. Any questions on how we're using that shift? So we're taking out that e to the 2t and replacing s with s plus 2. So now we got things in terms of things we know how to do. Don't forget to distribute here. 2s plus 7 over s squared plus 9. And in this case, we've got a denominator we know we can handle. Partial fraction decomposition is not going to get you anything on this. Why? Because the denominator is something we know how to handle, and the numerator is a proper fraction, right? It's 1 degree less. So now we can just apply linearity to it. We've got a sum of squares down here. That's a sine or a cosine. We got an s up top, so it's a cosine. Frequency is root 9, which is 3. Same thing here. We don't have an s, so it's a sine. If I took the Laplace of sine, I'd be multiplying by 3, so we divide by 3. And so it's up to you how you want to write this. I guess you could distribute through if you wanted to. Okay, there it is. Okay. Now, once again, where we're going with this is we're going to take an initial value problem, Laplace it over, do a bunch of algebra, and then Laplace it back. Okay? So in order for you to be ready for that, you got to be really good at Laplacing and inverse Laplacing. Okay? So tomorrow we're going to have a work day. Tune in with questions, and then we'll have office hours on Friday. Remember what Monday is. What's Monday, folks? Monday is the what? What's Monday? Here's the sun, and it gets blotted out. And so they canceled school for Monday, so no class on Monday. So then on Tuesday, we'll start actually solving differential equations with this, and you'll see how that goes down. Fair enough? All right, let's take a look at, for next week, just brief mention here as to what you got to do as far as tests and take-homes and nonsense. So test 11 is Laplace transforms. So test 11 is just, I'm sorry. Yeah, test 11 is Laplace transforms. So it's the basic formula is in the forward shift. So test 11 is over section 8.1. And then take home 11, there's a circuit on there. So that's from chapter 6. There's a circuit problem. And then there's more Laplace transforms. So there are no inverse Laplaces on the stuff due next week, just Laplaces. But when you do your inverse Laplaces to get ready for next week, you can check your answer by doing Laplaces. Okay. So yeah, so for so test 11 is basically section 8.1. Take home 11 is 6.3 along with 8.1. Okay. So if I don't see you tomorrow or Friday, have a great weekend. Be safe during the eclipse. Make sure if you're going to try to watch it, you've got the right glasses to do it. And we'll see you back here on Tuesday.